Okay, class has officially begun. Welcome to the electronics class. Like I said a minute ago, everybody please be sure you type into the text box, say hi or here or something, otherwise you won't get credit for being here. Before I start into the new stuff, are there any questions about last night's homework? Not seeing anything or hearing anything? All right. Well, I think it's really important that we go
Oh,
over the homework.
yeah.
Go ahead.
I'm sorry. Sorry. I didn't mean to unmute myself, but are we supposed to have cameras on for this Zoom call or no?
If I was you, I would want it off because it's being recorded. Um,
I see.
yeah, so you're
All right,
probably not going to want it to be recorded. I mean,
all
the
right.
very
Sounds
first
good.
day we did this, I had somebody who was sitting there and they were eating lunch and they didn't know that it was being recorded. So the whole,
Oh,
and I didn't notice it while I was taking the class because I was too busy thinking about the class, right? And
okay.
so afterwards I go look at the recording and then off in the corner, there's this guy sitting here eating lunch and it was really distracting. And he was really embarrassed afterwards, I'm sure.
All right.
Okay,
Okay. Sounds good. Good.
all right. Um, so what I'm going to do is I'm going to take a few minutes and talk about all of the homework problems just because I want to make sure that everybody fully understands them. So let's go into the electronics section. Okay. Now there's a few things on mine that you won't see on yours. So Ohm's law was the one that okay, come on. So Ohm's law was the one we did. And let me preview because my screen looks different from yours, but if I hit preview, then it looks a little bit more like what yours would look like. All right, now before we start into it, let's just talk about this little part right here. So this is something that the book does that, yeah, I'm not sure. I have mixed emotions about it. The book assumes that the person reading is not capable of doing basic algebra. And that is not the assumption that I have. Okay, so I like to just take one form of Ohm's law. And the form that I like is I like to think of it as I equals V over R. Now the book doesn't use V, they use E. So okay, let's use the book's form, E over R. Okay. Um, you should get used to seeing it both ways. But just to avoid confusion here, I'll do it the book's way. But you're going to find that most books actually use the letter V, not E. All right, and this is the way that I think is very easy for people to remember, because think about it. What is it? What is it that's pushing the electricity through the circuit? Well, the voltage is what's pushing it through the circuit. So it makes sense that if you increase the voltage, then the current would also increase. I mean, it just makes good sense to me. Okay, so all right. So if we've got the current is equal to E, boy, that's a horrible E. I think that's the worst one I've ever done, and that's saying a lot. So E over R. Okay, so it makes sense that as the current goes up, the voltage would. And what about the R? Well, the R works the exact opposite way because the R is what pushes back. All right. So if you increase the R, then the current is going to go down. So it makes sense that the R has to be on the bottom because otherwise, it wouldn't work that way. Right. All right. So once you have learned this form, then the rest of them you can just use your algebra skills. So let's say that I want to get what is the voltage. I want to get it by itself. So if you multiply both sides by R, okay, that cancels that, and you're left with E equals R times I. All right, which is this one up here. All right. And then what if you want to get R by itself? Well, okay, no problem. Just multiply or just divide both sides by I. So that cancels that. And you're left with R equals E over I, which is that one. And then the one that I started out was that one. Okay, so the people who wrote the book, they said, well, let's assume that the reader can't do basic algebra. So we've got this nifty little triangle here. And so we talked about last time about how it works, so I'm not going to go over it. So if you want to use the triangle, well, okay, but I would hope that you guys don't need the triangle. I would hope that you can do basic algebra. All righty. Here we have a simple circuit. We know that the voltage, which they're going to call E, is 12. We know R is that, so we want to know its current. So we know we're going to go I equals E over R. E is 12, R is 4. The answer is 3. Okay, but 3 what? All right, you'll see that we got, oops, keep forgetting before I try and move it. Okay, all right, you see that we got 3 possibilities here. It could be 3 amps, or it could be 3 coulombs. Hopefully you guys realize what a coulomb is, right? A coulomb of electrons is like a gallon of water, okay? It's a measure of quantity. So if I ask how much charge is there, if you say that it's 7 coulombs, that makes sense. But if I ask how much current is flowing, to say that 7 coulombs is the current flowing, that doesn't make sense. Okay, it would be like water. If I want to know how much water current is flowing in a creek near my home, if I say 7 gallons, that doesn't make sense. It has to be 7 gallons per second or 7 gallons per minute or something like that. So electricity is going to be measured in coulombs per second. So if the answer is just coulombs by itself, not coulombs per second, just coulombs by itself, then we know that that can't possibly be right. So the correct unit for current is amps. So the answer there is 3 amps. All right, question number 2. This one is a unit conversion problem. All right, so we start off with 28.3 milliamps. What we need to know is the conversion factor. We need to know how many milliamps equals an amp, all right? So hopefully you guys know that 1,000 milliamps equals 1 amp. This is something that you need to know really, really, really well. We're going to be using this a lot, right? So then so what we're going to do then is we're going to take the given quantity, we're going to put parentheses and a horizontal line, and if we got milliamps on top, that means we want 1,000 milliamps to be on the bottom, and then the other one goes on top, so 1 amp on top. So milliamps cancels milliamps, we're left with just amps. So the answer is 28.3 divided by 1,000 in amps, right? Dividing by 1,000, well, I don't need a calculator to do that. All I have to do is just move the decimal over. Let me switch to a different color. So if I divide by 1,000, that moves it over 1, 2, 3. So there's a decimal there. That means I have to put a 0 there. So the answer is 0.028. So I look at my choices there. And there we go down in the bottom. That's it right there, 0.028. All right. Now I realize that some of you are saying, why is Mr. Hendricks taking so long to explain this? This is all really clear. Well, I know from looking at your homework that it's actually not clear for some of you. In fact, several of you didn't get these right. And it was just the simple unit conversions that really messed you up. All right, so let's look at this situation here. We've got a battery, and this time we're using the symbolic representations. So this right here is the battery, and now when we're measuring the voltage, a lot of you are thinking, well, if we measure between here and here, then that'll tell us what the voltage on the battery is. But we measured it over here. Well, what you should realize is that whenever you have a wire, in this class, we are going to assume the wires have 0 resistance. Now, that is not really true. Wires actually do have some resistance. So there is going to be a slight voltage drop as you go along across a long wire. But this is the beginning electronics class. And so we don't want to get into that level of difficulty. If you go on and take an advanced electronics class, yeah, then you'll worry about that then. But for the beginning class, we are going to assume that all of the wires we deal with have zero resistance. And
Wait,
so that means that the voltage is going to be the same anywhere on here. So if I want to measure my voltage, okay, I can measure it. I can measure right here or here or here or here, and it doesn't matter. It's going to be the same. So when you see the voltage right here, that tells you that the voltage on the battery is 27, even though the terminal is not right here, but it's over here. As long as we just have solid wire in between them, it's the same. All right, and we can see that the current here is 0.41, and we don't know what the resistance is, so clearly that's what we want to do. All right, so what can we do? Well, we know that I equals V over R. That's the form that I like to remember it with. So let's just do a little bit of algebra. So if we multiply both sides by R, then that goes away. But then I've got an I there, so divide both sides by I. That's supposed to be an I on the bottom. All right, that goes away. So we're left with R equals V over I. So that means our R is 27 divided by 0.41. Get out the calculator, 27 divided by 0.41, and I get 65.85 and a bunch of others as well. All right, so all we have to do is, let's see if that matches our choices here. So 65.85, okay. All right, well, I don't see 65.85, but I do see something that's really close. I see 66. So remember, our answer was 65.85. All right, so you can see here that what we've done is we've rounded up. And speaking of rounding here, this is something that we haven't talked about before, but we should spend a little time talking about significant figures. Those of you who've taken a chemistry class know that Mr. Miller makes a big deal about significant figures, and good for him, because I do too in my physics class. So let's just talk about this really quickly. If I've got two numbers, if I've got 2.4 times 6.9537, okay, I want you guys to put that in your calculators and tell me what you get. And by the way, Eric, in answer to your question, this school does not teach an advanced electronics class, but we do talk about electronics in our physics class. And we do go into detail in the physics class about some things that we don't talk about in the electronics class, because in order to understand them, you have to know some physics first. And if you really are interested, if you take the U of U physics class, they go into some really cool electronics there. Okay, I don't see any numbers in the chat box here. You guys, you should have calculators with you. When you come to class, bring a calculator with you. So somebody type it out here. Still not seeing any answers. Are you guys awake? Or do you just not have calculators with you? Oh, okay, good. I'm glad to see somebody's awake. Okay, so Eric is saying that he got 16.688 repeating. Actually, the last little digit you got is a little different than, did I type it in wrong? When I type it in my calculator, what I get is 16.68888 repeating. Okay, good. That makes me reassured. Okay, so then what should I write as my answer? All right, so here is the rule that I'm going to go with in this class, and also it's the same rule that Mr. Miller is going to do in chemistry, same that I'm going to do in my physics class. If I look at this number, it's got 2 digits in it. And we're going to refer to these as significant figures. So if I've got a 2-digit number multiplied by a 5-digit number, well, the answer can't be more precise than the input numbers. And so this is my least precise input number. That means that my answer has to be no more precise than that. So if I've only got 2 digits in my least precise input number, I'm only allowed 2 digits in my output number. So I look at my number here and I need to either round it down to 16 or round it up to 17. I've got only those 2 choices. And clearly hope you guys agree that this number is closer to 17 than it is to 16. So I would report my answer as 17. And so that's what I've done over here on the left here. The answer on my calculator is 65.85, but my input numbers only had 2 digits in them. So that means I have to round off to only 2 digits, but I'm not going to just truncate, because if I go to 65, that would be going the wrong way. 66 is a closer number, so I'm going to round up to 66. So get used to it. In this class, we are going to be using this rule all the time. So if I've got a 2-digit number, multiply, so let's see what we had up here. Okay, so up here, you can see that we have, let me turn on my annotation. Our voltage here, 27.00, that actually has 4 digits in it. Now, some of you might say that those zeros don't count as digits. So we should talk about that in just a minute. Well, actually, let's talk about it right now. So if I've got 190, and I ask you how many significant figures there are in there, okay? Well, the 1 and the 9 are significant, but what about that 0? Is that really a significant digit? And the way that we do things in science is if that 0 is written right there, that is not a significant one. So 190 means that we think the real answer, so let's say that this is, I don't know, let's call it X, okay? If we write it as 190, that means that we are confident that X is somewhere between 185 and 195, okay? And on the left side, I'm going to make it less than or equal to, because if it was exactly 195, it would round up. But if it's 194.999, okay, then it rounds down. Okay, so if I write the number 190, some people might say, well, that has 3 digits in it. And my response would be, well, only 2 of those digits are really what we call significant digits. That 0 doesn't count as a significant digit. But over here, it's a little different over here. And I understand that this can be a little confusing. So let's think about it. If I've got the number 27.0, and then I've got another number over here that's 27, are those 2 numbers really different from each other? And the answer is no, they're not really different. I didn't need those zeros there as placeholders. I mean, like with 190, if I've got 19 and I've got 190, those 2 numbers are very different. That 0 makes the number 190 be very, very different from what it would be if that 0 wasn't there. 190 is a whole lot bigger than 19. So that 0 changes the number. We need it as a placeholder. But up here in the 27.00, did we really need it as a placeholder there? Okay. If I had just written the number 27 instead of 27.00, aren't those basically the same number? So I didn't really need those 2 zeros, okay? But if I put them there, I must have had a reason for putting them there. So if I write it as 27.00, that means that I am confident that the real voltage is somewhere between 26.995 and 27.005. Okay, that means that's what it means when I write those extra zeros. So in this case, if I write it like 27.00, this number has 4 sig figs. Okay, now look at this. My current here is 0.041. How many sig figs does that have? Okay, well, the 4 and the 1 are clearly significant, but is that 0 significant? If I have the number,
No.
yeah, I agree with you, it's not. If I have the number 0.41 and the number 0.41, aren't they really the same number? Okay. So, so that zero there doesn't really serve any purpose. So I've got two sig figs right here. So what I've got is I've got a 4 sig fig number, and I'm either going to multiply or divide by a 2 sig fig number. So what that means is in my final answer, I am only allowed to have two significant figures in my final answer. All right. Now, because I recognize that for some of you, this is brand new, I'm not going to be super strict about it at the very beginning here. If I were to give you a test and some of you were to write on the test that if you were to write the answer as being 65.85, for the first little while, I would not mark it wrong, even though I would prefer the answer be written as 66. If you were to write this, I won't mark it as wrong, okay? But if I give it to you as a multiple choice test, don't be surprised. This is the way you're going to see it over here, not this way. So just get used to that. And the sooner you get used to that, the better off you're going to be in your chemistry and your physics classes. All right, next one, we've got a number here, 7.3 kiloohms. All right, so hopefully now I don't really need to explain the details. I'm just going to make my parentheses, my horizontal line, and I need to know how many ohms is equal to a kiloohm. So I need to know that 1 kiloohm is 1,000 ohms. So kiloohms cancels kiloohms. So I'm multiplying by 1,000. So I take 7.3. If I multiply by 1,000, I move the decimal over 1, 2, 3. So here's my new decimal. That means I'm going to have a 0 here and a 0 there. So the answer then is 7,300 ohms. Okay, everybody good on this so far? Hopefully. If anybody has questions, speak up. If you don't speak up, I'll assume you don't have questions. But looking at your homework that you turned in last night, I know that several of you don't fully understand this. So speak up if you can. All right, so in this case now, what have we got? We've got R is 320 or 3.2 kiloohms. So 3.2 kiloohms. So again, we're going to have that 1 kiloohm is 1,000 ohms. So kiloohms cancels kiloohms. So this R is 3,200 ohms. Whenever you're using Ohm's law, you want to work in regular ohms, not kiloohms, regular volts, not kilovolts or millivolts, and same thing with amps. Whenever you're using Ohm's law, you don't want to work with the kilos and the millis and all that. That gets confusing. All right, so the I there is 538 milliamps. So 538 milliamps. And we know that 1,000 milliamps equals 1 amp. Milliamps cancels amps. So we're dividing by 1,000. So that means we're going to go 1, 2, 3. Okay, so the I then is 0.538. That's a 5. Okay, amps. Okay, so now all we have to do is figure out what the voltage is. So let me, oops. I wish there was an easier way to just erase a certain area there, but I'm not sure there is. All right, so we need to know which form of Ohm's law to use. So the form that I like to memorize is I equals V over R. So if I multiply both sides by R, then I get V equals R times I. So there we go. All right, so V equals R times I, and I know that this is R and this is I, okay? So 3,200 times 0.538. All right, so I get 1,721.6. Okay, and you'll see that that's not one of our choices, but it looks like maybe some rounding off was done. All right, so now the question then becomes how many sig figs are we allowed? So if you look, this number here has 2 sig figs. This number here has 3. So 2 sig figs is the rule. So I need to take this and round this off to 2 sig figs. So that means I'm either going to round down to 1,700 or I'm going to round up to 1,800. Which one of those is it closer to? Well, it's closer to this one than that one. So 1,700, there we go. That's our answer right there. Now, I realize that many of you got a perfect score in last night's quiz, and so you may be bored with what I'm going over right now. But guys, several of you did not get perfect scores on the quiz. So it's really important that we go over this. All right, so 192.6 microamps. All right, well, we know that there are 1 million microamps in an amp. Okay, so that means we're going to take this 1.92. So we need to move that decimal point over 1, 2, 3, 4, 5, 6. So there's our new decimal. So that means we're gonna have a 0 here. Yeah, oh boy, that was terrible. I need to make it bigger here. Let me make it bigger. Okay. So 192.6. So we need to move this over 1, 2, 3, 4, 5, 6. There's my decimal. So a 0, a 0, and a 0. Okay, so 3 zeros in front of the 196. All right. Well, looks to me like it's that one. Okay. You guys need to be really good at this. All right, now we got a circuit here, so we want to know how much resistance it needs to have. All right, so I'm going to start skipping around a little bit now. I'm going to start moving these a little bit faster. So if I equals V over R, then that means that R must equal V over I. Okay, I did a little skipping around there. All right, so if V is 12 and I is 46 microamps, well, it looks like we're going to have to do some conversion. So 46, whoa, that's terrible. So 46 microamps. Okay, so 1 amp is 1 million microamps. So we want to move the decimal over 6 times. So 46, move it over 1, 2, 3, 4, 5, 6. Okay, so it looks like we're going to have, looks like the answer is going to be 12 divided by that. Okay, so when I do 12 divided by that, I get 260,000 and change. So bingo, 260,000 would be 260 kilo ohms. And then the last one was you needed to build a circuit that has 1 battery, 1 resistor, add an ohm meter, and we want the ammeter to be 0.28. All right, well, let's go up here. So 1 battery, 1 resistor, an ammeter. Okay, and we've got too much. Okay, so we got 2 choices here. One is we could increase the amount of voltage, or I'm sorry, we could decrease. We could decrease the amount of voltage. But you see, it won't quite let us do it. The step size isn't quite right. We can either get 0.3 or we can get 0.25. So if the voltage is the only thing we play with, that's not going to do the job for us. Oh, so okay, let's change the resistance. All right. So if I've got 0.25 and I want 0.28, should I increase the resistance or decrease the resistance? Okay. Well, if I want the current to go up, that means I need to decrease the resistance. So there we are. Okay, so there's one combination that'll work right there. but hopefully you guys realize that that's only one of many ways that I could do it. Okay. I could up the voltage on the battery a lot, okay? But if I do that, that means I'm gonna have to up the resistance a lot. So there's an infinite combination of battery voltages and resistances that are gonna work, but only within a range. So you can see here, what have I done? I've kicked the voltage up to 51 volts, and even at maximum resistance here, I can't get it down to where we need to go. So it means I went too high on my voltage. So let's cut her back a little bit. Okay. Oh, look at that. I just perfect. I just totally by accident, I got it to the right one. So I didn't want to do that. Okay. So let's play with this now. Okay. So you see there's an infinite number of combinations of voltage and batteries, voltage and resistance that'll do the job for me here. So as long as you got the current down to what I wanted it to be, then you're good. All righty. So let me ask again. Now that you've seen the answers, those of you that didn't get perfect scores on your homework last night, which is quite a few of you, do you feel a little bit more comfortable now? So yes, no, give me thumbs up and give me some thumbs up or some sort of, okay, that works. All right. The rest of you don't want to chat, don't want to say anything? Okay, good. All right, so let's talk about tonight's homework then. Let's go into, okay. All right. Okay. Let's go into the electronics. And now when you scroll down, you're going to notice that we are now finished with what I called module 1. So we now have a good understanding of the basic concepts and the definitions, or at least I think we do. Now we're going to start in module 2. So now we're going to start doing something useful with these basic concepts that we know. So simple series circuits is what we're going to talk about today, and what your homework is going to be about tonight. Let me go to preview so it looks more similar to what you guys would actually see. All right. So again, you'll notice that I've pointed out 2 sections in the online textbook that I want you guys to read. So let me just close these up. All right. So if you go and you click on here, it talks about, so what are series circuits and what are parallel circuits? So I think it does a pretty good job of describing this. So a series circuit is when you have only one loop. You'll see that the electricity can only flow in one circle. Now, if we had another branch here, okay, so then the electricity would have 2 different ways that it could go, and it would not be a series circuit if that was the case. It's only going to be a series circuit if it has one loop and everything has to go through that loop. So whatever electricity flows through R1, all of that same electricity has to flow through R2. And all of that same electricity has to flow through the R3. And then all of that same electricity goes into the battery. Now, batteries, we can talk about as if the current flows through a battery, and that's actually not a bad way to think about it, okay? What's happening is the battery is receiving current in here and it's kicking electrons out there. What's happening inside the battery is a little bit more complicated. When you take chemistry, you'll learn more about that. But you can think of it as if the current is just flowing through the battery. That's actually not a bad way to think about it. So here you can see a circuit that is not a parallel circuit. Okay, in this case, we've got the electricity coming here. Some of it goes that way, but some of it doesn't. And then it comes to another branch. Some of that goes that way and some of it doesn't. So whenever you have more than one loop, we call that a parallel circuit. And we're not going to be doing homework problems with parallel circuits tonight, but we will next time we meet. Okay. So we're gonna focus just on series circuits. But there is one other type of circuit that you also need to know exists, okay? And this is called a series dash parallel circuit, okay? That's where you have these guys right here. These are, you see, these are parallel, okay? But we do also have another resistor right here, and this resistor here is hooked up in series with those. So all of the electricity has to flow through this guy. Now it breaks up into two different ways over here, and so this part of the circuit is the parallel part of the circuit, where some of the current flows through the left side, some of it flows to the right side. So because we don't have all of the current flowing through all of the resistors, we can't call it parallel. But over here, this one, all of the current does have to flow through that one resistor. Okay, so this, what you're seeing here is a combination of a series and a parallel circuit together. All right, and so a series connection. So this is even if you don't have an actual circuit. So we don't have a full circle. You know, normally we like to have a full circle there in order for it to be called a circuit. We don't have that. They're just connected up, but this is still called a series connection. All of the electricity that flows through this guy has to also flow through him and him and him. This is what we call a series connection, even though it's not a series circuit. Okay? And then same thing with down here. Okay, so this would be a parallel circuit because we don't have all of the current flow or all of the current flowing through each one. What we have is some of the current can flow through this guy, but some of it can go through that one, some of it can go that. Okay, so series and parallel, I would hope, are pretty clear. Let me just pause and make sure. Let me open up my chat box because when I share my screen, my chat box goes away. All right, so give me yays or nays. Does this make sense? So yes means this makes sense. No means you'd like to talk about it a little bit more. All right, I'm seeing lots of yeses. I'm not seeing any nos. Okay, good. So I'm going to skip over this then. All right. Well, that's it for this part of the thing. So now let's go back into here. Get rid of that. Okay, so you'll see that I've got another section of the textbook that I want you to read. And so now that we understand what series and parallel are, now what we're going to do is we're going to do some calculations. We're going to see if we can calculate what is the current, what is the resistance, what is the voltage. Okay. And the important thing is pretty well explained in this quote right here. The first principle to understand about series circuits, okay, the amount of current is the same everywhere. So whatever current is going through R1, the same current must be going through R2, and the same current must be going through R3. Because they're in series, we have the same current going through all of them. That is the key to doing tonight's homework problems, is you need to understand that. All right. Okay, so the very, very simplest circuit that we could possibly have is one resistor and one battery. And so if we know that I equals E over R, and we know here that R is 3 kilo-ohms, so that's 3,000 ohms, right? And we know that the voltage is 9 volts, or in this book, they like to say E equals 9. It's the same thing. So I is 9 divided by 3,000. So 9 divided by 3,000 is 0.003. And then some of you are going to say, wait a minute, our answer is 0.003. They say the answer is 3. What's the deal? Well, electricians don't like numbers that are less than 1 or greater than 1,000. So if they get an answer like this, 0.003, and by the way, that's going to come out in amps. Whenever you're using Ohm's law, remember, you can't work with milliamps or kilovolts. You have to work with regular amps, regular volts, regular ohms. So our answer came out as regular amps. Electricians don't like that, so because it's less than 1. So what they do then is they just convert the units. So they convert that into milliamps. That way they can give an answer that's somewhere between 1 and 1,000. So if you were to write the answer as 0.003 amps, I would not mark it wrong. But don't be surprised when you see the answer written as 3 milliamps. You need to recognize that they are in fact the same. All right. Now, if you have multiple resistors, then it gets a little bit more interesting. But it shouldn't be that hard, right? What we can do is we can recognize that 9 volts is the total for the whole circuit. So we got 9 volts here. That does not mean that 9 volts is the voltage across this resistor. So that's an equal sign with the line drawn through it. Okay. That does not mean that the voltage drop across this resistor is 9. The voltage drop across this resistor is going to be something less than 9 and something less than. In fact, what we're going to do here is let's figure it out. Let's figure out what is everything there is to know about this circuit. What's the current that's flowing through it? What's the voltage drop across each resistor? Let's figure out everything. All right. So if you've got a 3 kilo ohm resistor, a 10 kilo ohm resistor, and a 5 kilo ohm resistor, hopefully you guys recognize that the total resistance is just going to be the sum of those two. So it's going to be R1 plus R2 plus R3. So we got 3 kilo ohms plus 10 kilo ohms plus 5 kilo ohms. So that's 18 kilo ohms, which is 18,000 ohms. Whoops. Okay, so 18,000 ohms. That's the total resistance. This formula that I gave you right up here, this only works if they're connected in series. Tomorrow we're going to talk about parallel circuits. And so be careful, this formula that I gave you will not apply for parallel circuits. It only applies for series circuits. All right, so we know that our total resistance is 18,000 ohms, right? So our total is 18,000. V total is 9, okay? So we can use Ohm's law to figure out what the current is. So I equals V over R, okay? So that's 9 divided by 18,000. Okay, so get out the calculator, which guys, please get in the habit of bringing calculators. So 9 divided by 18,000. So I get 5e negative 4. And hopefully you guys have used your calculators enough to know that that means 5 times 10 to the negative 4, which is the same thing as 0.0005. Okay. All right. And so that is going to be how many amps we have. Right. Now, if you wanted to write that as milliamps, you'd have a problem, because if you divide that by 1,000, that's 0.5 milliamps, which is not a number between 1 and 1,000. So that's going to be the same thing as 500 microamps. Okay, so all of these are equivalent ways of writing it. Okay. All right, so if I were to ask you how much current is flowing through R1, the answer would be 0.0005 amps, or 500 milliamps. If I were to ask you how much current is flowing through R2, it would be the same, because in a series circuit, whatever flows through R1, the same current has to flow through R2, and the same current has to flow through I3. Okay? So if I wanted to make a note, if I want to say that the current flowing through R1 is 500 microamps, and I'd say, what's the current flowing through through number 2? It would be the same 500 microamps. And what is the current through 3? It is also the same 500 microamps. Okay. Now, what about the voltage drop? Okay. The voltage of the battery is 9 volts. Remember, that's pressure. So that means on this side of the battery, let me clear this out here. I don't want my drawing to be too cluttered. That means if the pressure on this side of the battery is 0 pressure units, the pressure on this side of the battery is going to be 9 pressure units. That does not mean that the voltage, that the pressure here is going to be because it's going to be 9. The pressure here is going to be some number less than 9. And the pressure here is going to be even less still. Okay. Every time that the electricity flows through a resistor, it loses voltage. But it's not going to go all the way from 9 to 0. It's going to go 9 to something less than 9. So what we need to do is we need to figure out what is the pressure at this part of the circuit. Well, we can do that because we now know that what the current is that's flowing through here. We know that the current is 500 microamps. Now, since we're going to be using Ohm's law, I recommend we write it as amps. Whenever you're using Ohm's law, you want to be using regular numbers, not micro or milli or whatever. So I'm going to write it as 0.0005 amps. Okay, so what we can do is we can use Ohm's law. So I'm going to use Ohm's law just for this resistor. So we know that I equals V over R. And I want to know what the voltage drop is. So what I'm going to do is I'm going to take that equation and I'm going to rearrange it. I'm going to multiply both sides by R. So that gives me V equals R times I. So this V is the voltage drop across R1. Don't worry, I do have a pen on order so that as soon as I get those pens, I won't have to write with my big fat finger here, so that my writing will be better. Okay, this is the voltage across R1. All right, so if I take the value of R1, which is 3 kiloohms, so that's 3,000, multiplied by the current that's flowing through R1, which is 0.0005, okay? So then 3,000 times 0.0005 equals 1.5, okay? So I'm going to write that as delta V just to help make it clear. This is the pressure drop that is only across this one resistor. So that means that, let me clear this out. So if the pressure on this side is 9 volts, the pressure on this side is going to be 9 minus whatever the drop was. So that means the pressure here is going to be 7.5. So delta V is 1.5 for this resistor. So the absolute voltage on this side is 9. The absolute voltage on this side must be 1.5 less than that. Does that make sense? So give me some yays or nays. So tell me yes or no. Does this make sense? One of the really hard things about being a teacher online is that I can't see your eyes. Okay, thank you for being honest there, for saying that it's half and half. I like that. Okay. If I was a teacher in the classroom, I could just look in your eyes and I could see whether or not this was making sense. But right now, I can't see your eyes. Okay. So those of you that are saying that it doesn't fully make sense, can you think of any questions that you could ask? Can you think of any questions you could ask that would help make it more clear to you? If not, let's just work a couple more examples. Maybe by working more examples, that'll make it more clear. All right, so we have decided that delta V, oops, I keep forgetting to turn this on before I do that. So for this resistor here, we said that delta V, which was I times R, was 1.5 volts. Okay, so the absolute voltage on the left side is 9. The absolute voltage on the right side is going to be 9 minus 1.5. So that means the absolute voltage right here is 7.5. So now I want to know what is the absolute voltage here. So I need to figure out what is delta V across R2. All right. So again, we know that delta V is I times R. We know what the current is through R2. We know that the current flowing through R2 is the same as the current flowing through R1, which we decided was 0.0005. But you'll notice that the resistance for R2 is different. The resistance for R2 is 10 kiloohms. So that, okay, so then if we then plug that into R and plug this in for I, so we get, what we get is 10,000, okay, times 0.0005, okay. So what we get here is that delta V in this case is 5. So remember delta, oh, maybe I didn't explain this, okay. So if I didn't explain what delta means, then shame on me. In my physics class, I use that term so much that I sometimes forget that people who aren't in the physics class don't know. Delta means the change in. So delta V means what's the difference between the left side of the resistor and the right side. Okay. So then, so what we've just calculated is that delta V here is 5, and what we calculated is, so that's delta V2, and up here delta V1 was 1.5, okay? And so then the only thing we need left is to find out what delta V is down here. Now there's two ways we could do this. One is we could recognize that the V total is 9. Okay, that's supposed to be a 9. That's a terrible, terrible 9. Boy, I can't wait to get my pen so that I don't have to write with my fat fingers. Okay, so one thing that we could do is to recognize that if the total voltage is 9, all of these delta V's over here have to add up to 9. So if I've got 5 and I've got 1.5 more, so that gives me 6.5. What more is it going to take me to get to 9? What is 9 minus 6.5? Okay, how about 2.5? Okay, now let's calculate it the other way and let's see if we get the same answer. Let's see. So if we know that I equals V over R, then we know that V must equal R times I. And we already figured out that I was 0.0005. Now for R for down here is 5,000. So 5,000 times 0.0005. Let's put that in our calculator. And hey, what do you know? We get the same answer. Okay, so delta V for that resistor is 2.5. All right, so see how this works? So we just calculated delta V for resistor 1 is 1.5 volts. Delta V for resistor 2, we said was 5 volts. And delta V for resistor 3, so delta V, sorry. Delta V for resistor 3 is 2.5, okay? And then V total, or delta V total, the voltage on the battery is 9. So you see these guys all add up to 9, which is reassuring because if they didn't, then that would be a problem. Okay, so Dallas, I see that you've got a question. And let me, when I share my screen, my chat box sometimes goes away. Okay, so Dallas, do you have a question? Go ahead and either unmute yourself or type it into the chat box. Oh, okay. I thought I got a little note there telling me that you had raised your hand, so I thought that's what it was. Okay, so hopefully this makes sense. So now let's scroll down to the last part here. They talk in here I think they do a really good job of explaining all this here. So it's not my job to read this to you. I'm going to let you guys read this yourself. But basically, everything that I said up here should apply. Now, this is an interesting method down here. They've got this thing they call the table method. All right. So let's look at what we just. In fact, let's go back up here. Let's take the example that we just got through working through. So let me make a note. Let me write this down. So R1 is 3 kilo ohms. R2 is 10 kilo ohms. And R3 is 5 kilo ohms. And V total is 9 volts. Okay. So one good way that they suggest here that I kind of like is let's use this table to keep track of all these things. So let's just go ahead and write into the table what we know the values are. So we've been given that R1 is 3,000, R2 is 10,000, R3 is 5,000, and the total voltage we know is 9, right? So if I were to just give you this table with these guys filled in, you guys should be able to fill in the rest. You should know that R total is equal to the sum of all the different R's. Okay, so 3,000 plus 1,000 plus 5,000 is 18,000. In fact, let me do this in a different color, just because I want to illustrate. So the blue numbers are the numbers that they were given. Let's switch to red. So the red numbers, those are the numbers that we calculate. So by adding R1, R2, and R3, we know that the total resistance must be 18,000. So now we can use Ohm's law to figure out what is the total amperage. Okay, so we know that I equals V over R. So the V is 9, the total R is 18,000. So that tells us that the total current is 0.0005. Okay, now if it is a series circuit, that means that the current has to be the same everywhere. If it's 0.05 anywhere, that means it's 0.005 everywhere. Now later when we talk about parallel circuits, that's going to be a little different. But for series circuits, that's why we start with series circuits, is because if we've only got one branch, that means the current in that branch has to be the same everywhere. Now that we know that, now we can use Ohm's law to figure out what is the voltage drop across each one of those guys. So we use the equation then, the V equals I times R. So we just multiply those guys out, and that'll tell us what the voltage is in here. And so that one worked out to be 1.5. And we multiply these guys out, and that worked out to be 5. And we multiply these guys out, and that worked out to be 2.5. Okay. And so we've now filled in all the tables. So in your homework tonight, I'm going to give you a problem like that where you need to fill in all the tables. Okay. Now, if you have problems here, let me suggest that you open up our nifty our circuit simulator. This circuit simulator, I think, is a great way to learn things. Okay, so if you're in doubt, just build a circuit and see what happens. All right, so we're going to have a battery, and we're going to connect it up to one resistor, and we're going to connect that up to another resistor. Now, some of you are going to say, well, hey, Mr. Hendricks, you really don't need to use these wires. You can just connect the resistors up without them. Yeah, I could. but I think for a lot of people, it's easier to understand if you do it this way. Okay, so here is the circuit that we just did. Okay, and so our total voltage was 9, right? So if I click on here, you can see the default is 9, so it's already there. We're already good. Okay, so this resistor here was 10 kilo ohms. Oh my goodness, we got a problem here. We can't go all the way to 10 kilo ohms. Okay, well, okay, let's just go to 10 ohms. And so our current here is going to be off by a factor of 1,000 because we can't go to 10 kilo ohms. So our resistance here, we're going to put it in as 10 ohms when we know it's really 10 kilo ohms. And same with resistor right here. Oh, I'm sorry. No, what was, oh, it was supposed to be 3. Sorry. This guy up here is supposed to be 3 kilo ohms. Okay. And this guy over here, he was supposed to be 10 kilo ohms. And this guy down here, he was supposed to be 5 kilo ohms. So because we can't go to kilo ohms, let's just go to regular ohms, right? And let's turn on the values there. So we got 3, we got 10, we got 5, all right? And so now if we want to know what the current is, we can just bring this guy over here and we can measure it. And you'll see here the current here is 0.5 amps. But remember that that's 1,000 times too much, okay? Because these resistors are only 1/1000th of what they should have been. So that means this current is 1,000 times too much. So really, imagine there's 3 zeros there. But the neat thing is, look where, it doesn't matter where I put this thing. The current is the same everywhere. Doesn't matter where I put it, the current is always the same. What about the voltage? Let's measure the voltage. We just got through calculating that the voltage drop across this guy on top was 1.5 volts. Let's see what happens here. Okay, now I got negative 1.5 because I put them this way. Look at that. You see how it shows that our calculations were right. Our voltage is 1.5 volts. Now, some of you might say, but wait a minute, Mr. Hendricks, it should be 3 kilo ohms and it's only 3 ohms. Well, it should also be less current than that. Why did our current go away? Oh, because it went over here. Okay. So the fact that our resistor is 1/1000th of what it should be is canceled out by the fact that our current is also 1,000 times more than it should be. So they cancel out. So we calculated that the voltage here should be 1.5, and hey, look at that, it is. All right, let's see what the voltage across this guy was. We calculated it should be 5. Hey, look at that, it actually is. And over here, we calculated that the voltage across this guy should have been 2.5. Hey, what do you know, it actually is. Okay, so this online circuit simulator that we have here is a wonderful tool. It has some limitations. You know, the main limitation is that when we change the resistance, 120 is the highest we can go. And it turns out that there's going to be a lot of problems where we want to use resistances that are way more than that. So what we'll have to do is we'll have to do this little trick that we did here. We'll have to use resistances that are 1/1000th of what they said it was. And then we have to recognize that the current we're going to get is going to be 1,000 times more than what it should be. But okay, so I realize I hit you with an awful lot of stuff just now, and it's just going to require a little bit of time for you guys to soak that all up. So let me just tell you that if you do the homework here, hopefully doing these problems that you see here will help make it clear for you. All right, so I'm going to cut it off here. Before you guys say bye in the chat box and disappear, does anybody want to ask any question? And if it'll help, what I'll do is I'll turn off the recording, because some of you might be hesitant to ask questions if you know it's being recorded. So here, I'll turn off the recording.